Since we talked about stuff, like real OS stuff. But we're going to move on. We're almost done talking about memory today. And Monday, I think, we will wrap up the memory part of the class, talking about swapping, moving stuff to disk and getting it back, and then also about page replacement algorithms. So we're sort of still moving our way up from the lower level memory management abstractions we talked about in terms of being able to actually translate addresses. Now we're in the kernel talking about how we move pages around and things like that. And then we'll talk about policies, right? So policy on Monday, which pages should be in memory, which pages should be moved to disk. All right, so including today, there are 11 days left for you to finish assignment 2. How many people have submitted a patch? OK. How many people are done? Ah, there we go. Sweet. Yeah, you were done like a month ago. How many people are done with assignment 3? OK. It's not too late for me to throw out an assignment 4 just for fun. There is an assignment 4, actually. OK, so we're going to start grading the midterm. I hope you guys will be patient. It's not going to be back next week. Next week is also assignment 2. I've got one set of TAs. How many people would prefer that the TAs help you with assignment 2 next week instead of grading? That's what I thought. That's what we're going to do. But we'll get to that as soon as assignment 2's in. All right. So last time we talked about data structures used in the kernel to store and retrieve page state efficiently. So we had this problem which is when the TLB needed help from the kernel to translate an address. We wanted to be able to locate information about that address quickly so we could tell the TLB what to do. Any questions about this? Does anyone even remember what we talked about? Like this was like before break. Wow, OK. OK, so page state. So why do we need to store state around? What are we going to keep up? What do we need to keep up to date? Why store the submission in the first place, Natasha?
The TLB up to date.
Yeah, we need to get the TLB up to date. What do we need to store? What information does the kernel need to store and be able to look up quickly? What's the lookup key? When the TLB has a problem, what does the kernel know? It knows the process it's running, right? It's scheduled that process. It better know which process is running on the CPU. What else does it know? Yeah, the TLB is going to tell me, hey, this is the virtual address that caused a problem, right? Please help me figure out how to translate this address or decide what to do, right? So we need to be able to store information about every virtual page, and we also need to be able to locate that information quickly, right? What else do we care about with these data structures? Yeah, Kevin. Yeah, we don't want them to get huge, right? Because these data structures are typically stored where? In memory, right? So this is pure overhead. Any memory we use to store this information is memory that I can't use for something useful, right? That's just the type of thing that processes don't notice, users don't notice, right? They'll notice if you do it badly, but the idea is to keep the overhead of these data structures small, right? So what do we need to store about every virtual page? What potentially do we need to know about this page when the TLB generates a fault? No. OK, Adam, this is your question. What's that?
The base address?
The physical address, right? Since we're talking about pages, we probably wouldn't call that a base address. What would we call it? Yeah, Doug.
A physical page.
Yeah, the physical page, right? So we might know the physical page, but what has to be true about this page if I have a physical page number for it, what does it mean about the page contents? Not a trick question. Where are they? They're in memory, right? So I need to know, where is the page, right? Where is this page? Is it in memory? We're going to talk today about cases where it might have been moved to disk. There's also a third case here. There's times where the process has requested permission to use virtual addresses, but those virtual addresses are just allocated by the kernel, but actually they're not backed with anything. There's no data for those addresses either in memory or on disk. Why would I do this? And what's an example of a case where this might happen? Yeah?
Someone might request for an allocation and not use it for a long time.
Well, what's an example of an allocation that the kernel might not fill in immediately? Yeah. What's that? No pointers are going to generate an exception, hopefully. What's a system call that might request memory that the kernel wouldn't have to, oh no, Kevin knows what it is, that the kernel wouldn't have to allocate immediately, but it would give it permission to use these addresses? Yeah. Oh, no, not quite. Fork does something even more clever. What about sbreak? So I ask for more heap, right? What are the contents of the heap when I ask for it initially? When I request more virtual memory to use as the heap, does that memory have any content? No. And it turns out that the kernel just fills in those pages with zeros, right? So what I can do is I can make some notes in my page table and say, by the way, I've given the process permission to use these virtual addresses as heap, but those pages don't exist yet, right? And I'm not going to create them until I need to. So it's possible that when I go to a page, I get a TLB fault, I go to the page table, I find out, oh, this is a valid virtual address, but this page doesn't exist anywhere. What do I need to do at that point, though? Need to find a page, right? Need to find a page in memory, need to clear that page out, and then I can return the physical address of that page, right? But it's possible that there are pages that are uninitialized. We'll talk about some of the process of doing that today. I also have permissions that I could apply on a per page basis, right? Hopefully you guys didn't get tripped up by the midterm question that asked you to make sure that you understood that permissions are applied to process virtual addresses, not to physical pages. You could have multiple virtual addresses pointing to the same physical memory with different permissions. There's no problem with that. And virtual addresses have to be applied, permissions have to be applied on a virtual address level. Because processes never receive physical addresses, right? And then when we start talking on Monday, we're going to start looking at statistics that the kernel wants to keep around in order to determine how often pages are accessed. Why would I care about this? Yeah. Yeah, so when we talk about page replacement, a lot of times, ideally, I want to use memory as a cache for the disk, meaning I want the stuff in memory that's frequently used and the stuff on disk that's rarely used, right? But I need to be able to measure that, and so I usually, kernels keep some statistics in the page table about how often pages are being accessed. We'll talk a little bit about limitations of this in a minute. And then, we talked about the requirements, which is that we want it to be compact, because the number of page tables grows as the total number of virtual pages allocated by every process on the system, right? So this can get very, very big. This is not bounded by memory, right? This is bounded by the total amount of virtual memory allocated by all processes, because every virtual page needs to have a page table entry. All right, I just gave that away, page table entry. What do we call, oh, this is an easy one. The data structure used to map a what to what is called a what? Virtual address, right? Virtual page number. What do I find for the virtual page number? Not the physical page number. What if it's on disk? What data structure do I find? Find the page table entry, right? And what do I call this thing? A page table. Yes, hint, big hint on the slide. OK. Every process has its own page table. Why? Why not just have one big page table for the entire system? Yeah.
Virtual addresses are common amongst.
Yeah, virtual addresses don't have any meaning outside of a process, right? I need both a process ID and a virtual address to map that virtual address, right? All right, so we talked about 3 different page table designs. There were these flat page tables. I could implement page tables as a linked list, and then I had these fun multi-level page tables. So the flat page tables, how fast are these? Oh, 1, right? Just a single lookup. How big are they? They're bad, They're very, very big, right? What about the linked list page tables? How long would it take me to look up an entry in one of these? N for n virtual pages, right? How big are they? They're good. They're N. They grow as the number of pages. That's good. What about, so these are too big, these are too slow. Multi-level page table speed. Yeah, it's better than log n. Constant, right? Whereas C is a constant that depends, well, it's just constant, right? But really the number depends on the depth of the page table. What about the size? I don't know how to figure this out. But essentially it's going to be larger than your linked list. but it's going to be smaller. It's probably log n. It depends on how the page. It really depends on how the pages are distributed, right? The nice thing is because process address spaces are usually fairly sparse, you can usually it's better than it would be if pages were distributed at random. Pages are distributed at random would probably be log n, but because they're not, because they tend to be clustered in little areas, it's better than that, right? All right. Any questions about this stuff now that I've refreshed your memories, Adam?
So the multi-level page table isn't necessarily a tree?
I mean, it is a tree of sorts. Yeah, I mean, it is a tree. It's a tree that has a limited depth.
Okay.
Yeah, but it's a tree. Yeah, yeah, definitely.
Isn't it log n less than that?
With the number of allocated pages. So it doesn't. The linked list grows with n, right? The size, and I think that that's a good. Yeah, that's a good question. You're probably right. Anyway, don't quote me on that. I'm bad at these sort of. I actually never took a course on algorithms. Never. That's because I wasn't a real computer science major. So, okay. Any other questions about this stuff that I can answer? Not the ones I can't. All right. So today we're gonna. I mean, we've been hinting at this for a while. I think we talked a little bit about this last time. But pages don't always stay in memory, right? And we call the process of moving pages back and forth between memory and the disk swapping. And the reason we do this is because we want to be able to borrow disk so that we can create more memory, right? If I can move sort of underutilized memory out to disk, I can preserve the memory interface since the contents don't change, but I can use that memory for something more useful, right? And this is done for a couple of reasons. I mean, the main reason it's done is because processes don't always make good use of their memory. They allocate a lot of stuff that never gets used. Or they allocate it, they use it a little bit, and then they don't free it. They forget to put it away, whatever, right? And so to deal with these issues, we can move this stuff to disk, right? It frees up more memory for useful things. And again, when we do swapping well, your system feels like it has sort of, like all the memory plus swap is memory, right? It all feels as fast as memory because all of the accesses to pages, or a very, very large number of page accesses, are being soaked up by the quote-unquote cache, meaning memory, right? So if I manage my cache well, most of page accesses hit in my cache, meaning memory. If I manage it poorly, then it's possible that most of them hit in the disk, which now makes it look like I have a combined memory swap area that is all as slow as disk, right? And disk is like at least several orders of magnitude slower than memory. Even with your fancy new flash drives, it's slower than memory. Right? It's better, but not that good, right? And this is what we don't want, right? We don't want to feel like I only have as much RAM and it's all as slow as disk, right? This is bad. Okay, so what do I have to do? Let's say I have a page. I found my candidate page, and we'll talk on Monday about how I locate pages to replace when I need memory. But let's say I found one. Let's come back to that on Monday. What do I need to do? What are the steps that are involved here to move a page to disk? I've got a page of memory. I want to move that page to disk. I'm going to remove it from memory. What are the things I need to do here in any particular order? Yeah, what's one of them? Yeah, so that's really important, actually. And I guarantee when you guys do assignment 3, you'll probably make every one of these mistakes, right? So the common mistake is forgetting to clear the TLB. If you do that, so what happens if I don't clear the TLB? Kevin? Yeah, so eventually the point is whatever is in this physical page, I'm going to move to disk. Then I'm going to do something else with that memory, right? And so if I let that translation stick around for too long, it's possible that whatever I was doing first is going to end up getting mixed with whatever I'm doing next, right? And it turns out, actually, that this is the first thing I have to do when I swap out memory. Why is that? I mean, I have a better idea. Let's just copy the contents to the disk, and then when I'm done with that, then I'll take the TLB entry out. Seems like that's, that'd be better. Yeah, Brandon, why does that work?
With something try to, like the process, try to access that translation, would that cause an issue?
No, I haven't given this page to another process yet. So that's safe. It's still only going to be accessed by the process that was originally able to map this memory. Doug, what's going to happen?
It might try to access the memory while you're changing it.
Well, but I'm not changing it, right? I'm writing this page out to disk. I'm not going to alter it. Yeah.
The process writes that copy and then that's not going to be written to disk.
Yeah, if the process starts altering the page as the page is being written out to disk, you know, I don't know, 50-50 chance that that change is going to make it onto disk, right? So now I have memory that's not obeying the memory interface anymore. Memory's not supposed to go back in time, right? It's not supposed to be like, oh, when I do a load, I'm going to give you the story you did a few minutes ago, right? That's not how memory works. So I need to get the translation out of the TLB first, right? Once this is done and there's nobody else who's able to access the page, right? No user processes should be able to access this page. Then I can start moving the page to disk, right? All right, so now what's the next thing I need to do? Yeah, sorry.
Can you not keep the writes in a buffer and actually implement them, sort of,
Where would the buffer be?
on memory?
Yeah, so now you need another page, right? Yeah. I mean, you could do that, but now you've created, now you kind of recursive swap out, right? Now you have to find another page. Right? Pretty soon, your whole memory is buffering pages that you're trying to get to disk, right? So no, it's simply, I mean, it's a clever idea, but it's simpler just to get things out of the TLB, right? Make sure the process can't use it. And this causes a lot of headaches, right? You guys will have to think about this hard once you start assignment 3, because what can happen here is I can remove the translation for the TLB, but and when I'm in the middle of swapping the page out, the process can fault on that page again, right? And so now what do? I've got a page that's like halfway between memory and disk. Yeah, it's a mess. OK, and this is, what's that? Yeah, but what if you're trying to use it? You know. So this is one of the reasons actually that page replacement is so important, right? If I pick the wrong page, we'll talk about this on Monday, then it's possible that it's coming right back into memory, right? If I pick a page that's very heavily used, the next thing I'm going to do after I swap it out is swap it right back in, right? And I end up paying 2 IOs to go to disk for basically 0 extra memory, right? So that's terrible. Again, we'll get back to this on Monday. I don't want to get too ahead of myself. Yeah?
When the kernel is clearing the TLB, the address, then the kernel is in privilege mode, right?
Right, you're the kernel,
Yeah.
right? If the kernel is running, then you're in privilege mode, right?
So how can the process do a write to the TLB when it is not running? Because it's not returned to the user mode yet.
OK, so when I start copying the contents of page to disk, what's going to happen? So right, let's say the kernel ran and it removed the translation. So now he's saying, yeah, the process isn't running, it can't. But what happens now? Yeah.
Don't you possibly switch to another process since it takes a long time?
Yeah, this takes forever, right? These IOs. So as soon as I initiate this IO, the kernel is going to get out of the way and let something else run, right? If that something else is the process that I just kicked a page out for, and I haven't removed the TLB entry, right? There's another complication here. Can you guys? So this is sort of like these are circa 1980 slides, yeah.
You had the process running on a different core.
Yeah, what do I do about other cores? Every core has its own TLB, so it's possible that this page is actually mapped in another core's TLB. If you look at your system, there's something that you have to do during page eviction called TLB shootdown, which is pretty much what it sounds like. You have to find a way to get any entries that might map to that page out of the TLB of every other core, right? And this turns out to get nasty because you have to communicate with the other cores, et cetera. I think I talked about that at some point, maybe not today. OK, so now I'm going to copy the contents of page to disk. And finally, I'm going to update the page table entry to indicate that where the page is, right? If I don't do this, what happens next? I put the page on disk. Sweet, I've got some extra memory. When am I going to regret not writing down where I put it? The next time I try to find it, right? Oh, where'd it go? Ah, whatever. Just give you some zeros back. That won't break anything. Yeah, OK. Now, check this out. Oh, these are some of my favorite animations all semester. I shouldn't have spent so much time on that slide, because look at this awesome picture. All right, so yeah, this is like going for Matt Welch style complexity here. OK, so I've got my address space, and let's say this process is in the process of this process is using this page. It's mapped in the TLB. It points to this piece of physical memory, and I want to perform a swap out, right? So lightning review. What's the first thing I have to do? Get this entry out of the TLB, right? Once I've done that, then I know that the process isn't going to use this. That's not quite true, right? But what will happen if the process tries to access this page now? It'll generate a fault, right? And then I'll be stuck with the problem to solve, right? But at least the process can't change or access the page behind my back as I'm trying to copy it out, right? So now I copy the contents of my page to disk very slowly. Now what do I need to do? Third step. I heard clear. I don't like that. That scares me. Clear. What do I want to do? Yeah. Update the page table entry. Right. The page table entry has to know where the page is. Right. Now I'm done. Cool. So let's think about the relative time frame of each one of these operations. How much time does it take to remove the TLB entry? It's fast, right? What about copying the contents of the page to disk? It's a very slow operation, right? And then what about updating the page table entry? Should be pretty fast. Yeah, you have to find it. Stuff like that. And this is interesting, right? So what's the slow part of this? The copy, right? How can I make that copy unnecessary? In what case? There's a very, very nice case. You've answered too many questions. You're done. There's a very, very nice case when I don't have to copy the page to disk. What is it?
The disk already have a copy.
Yeah, the disk already has. Wouldn't that be awesome if there was a copy of that exact page sitting on disk? How do I get that to happen? So there's this process called page cleaning. So I don't know, you guys probably are as dorky as I am, but I used to have a computer. I still do, but it's a different computer. And in college, and it was next to my bed, where all computer scientists put their computers. And at night, it's really irritating because the disk would, constantly, right? Just constantly making this little noise. And I wasn't doing anything with the computer. It was sitting there, right? And now I had shut down my illegal, MP3 sharing operation a few years back. So there was nothing happening. It was just, what is happening, right? So it turns out that kernels are constantly going through pages and trying to get them to disk, right? Particularly when there's nothing going on. If you have some idle cycles or you have some time where the user walks away or isn't using the machine, try to synchronize the copy of memory with the contents of disk, right? And the reason is, one requirement for doing this is each page has to have sort of a dedicated spot on disk. Not necessarily dedicated, but the idea is that each page has to exist both in memory and on disk, right? Sometimes the page will only be on disk. Sometimes there'll be space for it both in disk and in memory. But there has to be somewhere to write it to, even when I'm not moving it out, right? And again, during idle periods, I just sort of walk through pages on the system, find pages that are dirty. How do I do that? Write them to disk, right? That means that hopefully, when I actually need a page, I can find a page that's already synchronized with its on-disk copy, and I don't actually have to copy the contents. And we call pages that have matching contents on the swap file or on the swap disk clean, right? And the other ones are dirty, right? A little bit of pejorative language here, but anyway. So now I can do this only if the page is dirty, and this is nice, right? Here's a question. How do I track when pages get dirty? How can I tell? I mean, they don't look dirty, sadly, right? If you go, that's a dirty page, It's got some mud on it. How do I tell when the page gets dirty? Yeah. Okay. Who's going to set that? I could certainly have a bit in the page table entry that says the page is dirty. So that's how I record that the page is dirty. How do I find out that the page got dirty? But when? So I have an idea. Every time the process writes to the page, I'll set that bit. Is that a good idea? No. It's going to be terrible, right? The system is going to slow to a crawl. So does anyone remember? There was a way that the TLB was going to help us here. Yeah. Well, okay, you're going in the right direction. It has to do with permissions, yeah.
Usually we write the mapping with the read permission only. So when process trying to write the memory, then it has a TLB fault. The kernel keeps track of what is getting updated.
Yeah, exactly. So I can use, remember that the TLB potentially had this way to mark a page as read-only. And we talked, I think, before a break about, or actually one of the exam questions had this on it, where the ones we went over on Monday, where it said, why is this page in the TLB, the page table entry says it's read-write, the TLB says it's read-only. One of the reasons that you do that sometimes is so you can see writes, right? And the nice thing is, you only see the first write, right? But that's good, because it only takes one write to make a page dirty, right? Once a page is written to, you just have to assume that it doesn't match its contents on disk anymore. So it's possible that the way that the kernel sets this up is I load it in read-only, right? Now I see a write fault. I see the first one. I don't have to see every one. There's a little bit of overhead to this process. I set the bit. When does the bit get cleared? Yeah, during cleaning, right? When I've successfully written the page to disk, I can clear the bit, right? And there's some synchronization issues with doing this properly. You have to be careful about. Can I clean a page? Here's a good question. Can I clean a page that's in the TLB? Would I want to clean a page that's actively mapped in the TLB? Probably not. I mean, you could write it out, but who knows what ends up out in disk, particularly if it's mapped to read-write in the TLB, because there could be active modifications going on. And if I'm starting at one end and writing to the other, then I get some mix of the front and the back, and that page is totally worthless. Right? So a lot of times I try to avoid cleaning pages that are in the TLB, or I remove them from the TLB while I'm cleaning them, just to make sure that they don't change. All right, so yeah, so now I can optimize this process. Okay, so now I've got the page on disk, and hopefully it stays there for as long as possible, right? This is the goal, and we'll come back to this on Monday, but you have to think about it. This sounds great, right? This whole idea of like writing pages out to disk, it's so cool, but that actually creates a lot of overhead, right? I mean, moving a page to disk is a very sort of I/O intensive operation, and it slows down the machine. It makes that page inaccessible for a period of time. My hope is that this swap in never happens. I mean, that's the ideal page, right? But hopefully that page stays out for a while. Now I need to swap it in, right? So what do I need to do? So first of all, what is going to trigger? What specific thing is going to trigger the swap in process? A TLB fault, right? So, and that's going to be generated by a what? Like a load or store to an address on this page, right? So the process loads, and keep in mind, the process has no idea that this page is not in memory anymore, right? It's just minding its own business, and I'm pulling pages out from behind it, right? Because I've created this level of indirection allowing me to do that. Now the page is on disk. Process is like, hey, I'm going to use that memory I was using 10 minutes ago, right? The kernel's like, uh-oh. Load or store is executed. First thing I need to do is make sure to stop the instruction, right? So the exception that the TLB generates essentially stops the instruction. But this process cannot run again until I figure out what to do, until I get that stuff back into memory, right? So this process is actually swapping out, I do behind a process's back, right? The process doesn't know what's happening. Swapping in is something that actually stops the process from executing for a minute while I go get the contents, right? So this is something that's actually going to have a performance impact, and that's another reason why it's very important to pick the right pages to move out to disk, right? Okay, so what's the next thing I need to do? Well, there's a couple of things that need to be done. They don't need to necessarily be done in a particular order, but what's one of the things I need to do?
Find the page.
Find the page. I better have written down where this page is. So I need to find the page in the swap file or on the swap disk that holds the contents of this virtual page, right? What else am I going to need, though? Kevin? Yeah, I better get a page of memory. So what could a swap in generate? Oh, man, this gets terrible, right? So now I'm trying to swap in a page, and I'm like, uh-oh, memory's full. Got to swap something out, right? Another good reason to do page cleaning. Hopefully, if I have a clean page, I can just drop it, mark it on disk, and I have a page immediately. But it's possible that the swap in process can actually generate another swapping operation, right? So I've got to allocate this page to hold the new page contents. I have to locate the page on disk. Now what? These are not trick questions. It's pretty basic, Doug.
Tell the TLB where it is.
But is it there yet?
Oh, well, put it there.
Put it there, right? Yeah. Come on. There's like 7 steps here. You think I would have missed that one? Yeah, I got to copy the contents in from disk, right? I have to fill the memory that I've allocated. Now I need to update the page table entry, right? That's really important because the page is no longer on disk. It's in memory now. And now I can restart the instruction. Well, load the TLB and then restart the instruction. Right? Does this make sense to everybody? Just in case it didn't. Right. So now I've got my page on disk. Process executes a load. The TLB, I wish I had my little TLB question mark, does not know what to do. The kernel is going to figure out, oh, this page is on disk. Going back to the beginning of class, what else could, well, never mind. It doesn't make any sense. Sorry. So I need to find a page in physical memory. Hopefully I have some memory free at this point. Write the page in, and then update the page table entry, load the TLB, and then restart the instruction. Right? This is a little bit of a more complicated operation, partly because it occurs in the process of performing an instruction. So, am I done already? Oh gosh. Maybe I should just pull up the next lecture and we can keep going. Oh wait, no, I have some other stuff. Good. Okay, so yeah, we'll talk about this on Monday. Great. I think we talked about TLB and page faults before, but we distinguish between these 2 types of faults, right? So a TLB fault means that the page is not in the TLB but is in memory. A page fault means that the page is not in memory or hasn't been initialized. Essentially, if I need to find a page of memory, then this is a page fault and not a TLB fault, right? If the page is already in memory and all I have to do is update the TLB, then this is a TLB fault, right? And every page fault is, by definition, preceded by a TLB fault. But not every TLB fault generates a page fault. So here's another, I knew we had to talk about something else cool today. So here is another system design principle, all right? Which is that sometimes procrastination can be helpful. If you so let me distinguish between 2 types of procrastination. There's procrastination about things that you know you're going to have to do, right? Like assignment 2, right? Or assignment 3, right? And then there's procrastination about things that if you wait long enough, they just might not ever need to get done, right? So, there's no point doing stuff now that you might have to never do, right? There is the point doing stuff now when you know you're going to have to do it. And kernels take advantage of this process because frequently apps and processes don't know what they're going to do. And so they make these requests for things that it turns out if I handle them right up front, I may create a lot of load on the system that I don't need to. Right? So for example, process executables, like a big complicated executable probably contains massive gobs of code, right? And when exec runs, it says, hey, here's how I want my address space laid out. I have a gigabyte of code that I want you to put right there, right? And the kernel is like, no, not going to do that, right? Why not? I mean, it has stuff it wants in its address space. Come on. Why can't I get away with this? There's 2 reasons. Adam, what's one of them?
The kernel might doubt if they actually use all that space.
Okay, so I might not, and how would I not use it, particularly for a code region? What does that mean? Yeah.
It just means you're executing one instruction at a time from that code, so it'll take a long time to go through the whole.
Well, I mean, even if I was executing, if it was one long function, that would be awesome, right? If you wrote your program as like one huge function that had no conditionals, breakpoints, loops, then you would just, it would take a long time to get to the bottom. That would be interesting. But what's probably more true in general?
Locality.
Not even locality.
There are some branches that are never executed.
Okay, so there might be some dead code, right? That's kind of a really sort of corner case. There might be some code that's actually unreachable, but there's also some code that's never reached by you, right? Again, there's features of apps. There's things that, that are built into apps that aren't features that you use actively, that you may have never used. There are probably, it'd be interesting to find this out, but my guess is that for most of the apps that you guys use, there are code paths that you've never been on. Never, right? And you may never go on them, right? You may not care. There may be a feature that you just cannot find. All the help documents, or maybe it's like Firefox support, I know. And Firefox is a code that you guys never execute, I'm sure, but but Chrome code, right, to handle old, weird, broken dialects of HTML, right? HTML 0.1 or something, right? That code may never be executed. So there's a lot of code that isn't used by processes. Here's another example, right? I want this big chunk of heap, right? Like malloc, I have a malloc implementation that just requests big, huge gobs of memory, right? And the kernel is like, yeah, I'm going to I'm going to make a note of the fact that you asked for this, and I gave you permission to use it. But when you actually need it, why don't we talk again? Yeah, Scott.
Processes ever relinquish their heap if they don't need it?
Yeah, you can actually make negative S-break calls. Does anyone think that actually ever happens? So this is a good question. The answer is actually quite complicated, right? Because if you think about how malloc works, right? In order to move the breakpoint down, I need free memory at the very end of my heap, right? But it turns out that the way the objects are allocated means that a lot of pages are probably still in use, right? There might be an empty page in the middle, but there's no way for the process just to get rid of that one page. Hopefully, what happens to that one page eventually? Let's say I have a page of memory in the middle of my heap that's never going to be used again. Where should that page go? To disk and stay there, right? Go to swap and stay there forever, right? Until the process dies, at which point I can get rid of it. So now, in the first case, let me ask another question, which is, why can the kernel get away with doing this? Again, I ran exec, and exec told me I've got this big blob of code I want right there, and the kernel's like, I'm not going to do that, right? I'm not just going to put the code. What does the kernel need to be able to do in order to play this game? Yeah.
Not load that HTML entry into the TLB.
Well, right, I'm not going to map that memory yet. But let's say the process starts to run that code. Then what do I do? Need to go get it. But where is it? It's in the executable file, right? So as long as I'm careful, the point is I need to be able to find it later, right? If I don't put it in memory, I sure as heck better be able to find it in the file later, right? So it means that it's possible that a page fault may actually cause the kernel to go get some pages from an executable file, right? So here's the executable you were running. Oh, okay, you asked for that code page. Oh, I know where that is, right? So it's a form of swapping, but it's actually not in the swap file. So essentially, what on-demand paging on-demand paging means that until you actually use parts of your address space, kernels feel no responsibility to actually back that memory with anything useful, right? If it's code, when you use it, I'll go find it. If it's heap, when you use it, I'll go allocate it. And again, the reason for this is that a lot of code is never executed, and even a lot of global state that processes might use, right? So not just code, like shared variables, right? I mean, a lot of those shared variables are used by the same code paths that you're not going down, right? So why use all this memory? So if you guys use an application that has a pretty complicated executable, you probably notice that when you start up, I mean, it doesn't the system doesn't sit there for 10 minutes loading it, right? I mean, if you loaded every page in Photoshop into memory when it booted, you would be there for a while, right? You'd be there a long time. And so as you're going around and you hit menus, things sort of come in as they're needed, right? But a lot of this stuff doesn't get used. So the first time I executed an instruction from a new code page, I've got to go get that page. What about these uninitialized heap stack or data pages? You guys remember what happens to them? Stack is the same way, right? So as my stack grows downward, right, as I make more function calls and need more stack space, the kernel is allocating stack on behalf of the process as well, right? Stack is a little different than the other memory allocations that we talked about because it's done implicitly. There's no system call that I use to allocate stack, right? It just happens because my stack has walked down to the page below where it was before. But in all these cases, what do? What am I going to give the process? It allocated some heap, and now it's trying to use it. What do I need to put behind that request? Man, you guys must be tired. Yeah, just give it zeros. You know, give it I find a new page, fill it with blankness, and give it to you. Right? Yeah, it's pretty simple. Did we already talk about hardware and software managed TLBs? Is that a question on my meeting exams? I think I've hinted at this, right? So let me just cover this, and then we'll be done for today. So there are certain architectures, and I just need to make sure I introduce this to you. My old advisor used to do this whole, maybe I should give this lecture because it's kind of fun. He used to do this whole lecture on x86 memory management, and it's really gooey, right? The MIPS architecture we asked you guys to use for OS 161 was chosen partly because it has a very nice, clean memory management system. Real architectures are considerably more complex, right? And one of the complexities comes from the fact that on certain systems, the memory manager is smart enough to actually look through the page tables by itself. So when I get a fault, right? So the architecture we've been talking about so far, if I can't locate the page in the TLB, what happens? I ask the kernel for help, right? I generate an exception. On a hardware managed TLB, what actually happens is the hardware will look through the process's page tables. It'll walk the process's page tables. If it finds a translation to a page that's in memory, it will load that translation itself. If it doesn't, what happens? Then it asks the kernel for help, right? So what kind of faults do we not see on a hardware managed TLB? TLB faults, right? Because the TLB faults are all handled internally by hardware, right? So what's a pro of this approach? Why would you implement this?
Fast, you don't have to involve the kernel as much.
Yeah, so I can handle I can handle TLB faults myself without trapping into the kernel, right? So that's nice, and hardware is faster at doing this, right, obviously. And part of the speed advantage just simply becomes not having to trap into the kernel, right? So that's nice. What's a con of this approach? What's that? Somebody mumbled something. Yeah.
The kernel is unaware of any TLB.
Yeah, so that's one good point, right? Which is that the kernel doesn't see TLB faults, and in certain cases that can cause problem with statistics, and that means that the hardware has to help us, right? But what else does this do?
There has to be some agreement between hardware and software on how to implement page tables.
Yeah, the operating system has to set up page tables in a fixed way that the hardware understands. So the hardware, unfortunately, you know, this is the hardware. This is what you get when you negotiate with hardware, right? Hardware is like, I can help you with this, but I'm really dumb, right? And so the only way I can help you is if you do things exactly the way that I want them done, right? And also, I'm very inflexible, right? So yeah, the operating system essentially has to set up the page tables exactly the way that hardware wants, right? And so on x86 type systems that use these hardware TLB architectures, there's really no way to change the page table structure, right? The hardware is in charge of how this looks. And as someone pointed out, the kernel never sees the TLB faults at all handled with hardware. All right. And yes, don't worry, you have a software managed TLB, so you can design your own page tables, which, to be honest with you, sounds like more work, but is actually probably easier than having to figure out what hardware wants and give it what it wants, right? Okay, so on Monday, we will talk about page replacement algorithms. And that will be essentially the end of the virtual memory unit. Work on assignment 2.